Today's lecture is going to start us off with Chapter 8. We're going to go through two sections on Chapter 8, counting by weighing and atomic masses. And you'll notice on the lecture that deals with 8.3, we end up with the huge concept in chemistry that we need to learn about, and that's called the mole, and that's what that is right here. And we'll start that on the next lecture. So today we're going to be looking at counting by weighing and atomic masses, counting atoms by weighing. So let's go ahead and get started there. Objects don't need to have identical masses to be counted by weighing. We need to know just the average mass of the object, and to count the atoms in a sample of a given element by weighing, we must know the mass of the sample and the average mass for that element. All right, let's look at an example of what I'm talking about when I say that you don't have to know. What is the mass of 1,000 jelly beans? If I ask you this question, you would not count out 1,000 jelly beans and take the mass of them. So what we need to know is that there's an average mass of 1 jelly bean. If we know that, we can calculate the mass of 1,000 jelly beans on average. Not all jelly beans have the same masses. Suppose we weigh 10, and this is the information that we find. You notice a little bit of variance in the masses of the jelly beans. Now we can find the average mass of a jelly bean by finding the average or the mean, which is something you're very familiar with in your algebra classes. And we find out that the average mass of 1 jelly bean is about 5 grams. Then we can multiply 5 times 1,000 and get 5,000 grams to know the mass of 1,000 jelly beans. Let's look at averaging the mass of different objects. Two samples containing different types of components, so type A and type B, both contain the same number of components if the ratio of the sample masses is the same as the ratio of the masses of the individual components in the container. Let's look at an example of how we can apply that. We're going to use something that solves a whole lot of problems, not just in chemistry, but in everyday life, and it's called ratios and proportions. Okay, the problem says we have a pile of marbles, and those marbles weigh 394.8 grams. I know that 10 marbles weigh 37.6 grams. How many marbles are in the pile? So what we're going to do is set up a ratio, and we're going to say if 10 marbles, marb for short, weigh 37.60 grams, then how many marbles is going to be in the mass of 394.80 grams? And the previous slide, this is just giving us some number values to understand what the previous slide was actually saying. So we're going to cross multiply, which we're going to do a lot in this class. So 10 marbles times, remember when we cross multiply, we do this and set equal to this. So 394.80 grams equals X times 37.60 grams. We're going to divide both sides by 37.60. And you're going to notice when you do that, our grams are going to cancel, and we're going to be left with marbles, which is what we want. So let's do the math real quick. So we have X equals 105 marbles. And we know that because of the information given for 10 marbles, we can do the ratio to find how many marbles are in almost 400 grams instead. So that's one way to use ratios and proportions to solve a problem like we're going to be solving in this chapter. So that's great when we talk about marbles and jelly beans, but how does this make any difference when it comes to atoms in chemistry class? So atoms have very tiny masses, so scientists made a unit to avoid using very small numbers. So one atomic mass unit, also known as the AMU, is equal to 1.66 times 10 to the negative 24th grams. The average atomic mass for an element is the weighted average of the masses of all the isotopes of that element. So we talked about this in a previous chapter, that that's why we have a decimal point after the masses. They're average masses because all of the atoms on the periodic, or elements on the periodic chart, have same number of protons and electrons for a particular atom, but different numbers of neutrons, leading to isotopes. So it's just something that we're going to bring back from a previous chapter. Even though natural carbon does not contain a single atom with a mass of 12.01, and this number is off the atomic mass on your periodic chart, for our purposes we can consider carbon to be composed of only one type of atom with a mass of 12.01. So we know that there's no carbon atom that exists that has a mass of 12.01, but that's our average, and that's what we're going to go with when we talk about carbon atoms. This is going to enable us to count atoms of natural carbon by weighing a sample of carbon. Calculate the mass in atomic mass units of 431 atoms of carbon. So the mass of one carbon atom, if you look at the periodic table, you'll find the mass is 12.01 atomic mass units. Use that relationship as a conversion factor. Remember, from previous experience, we can say one carbon atom over 12.01 AMUs, or we can flip that and use 12.01 AMUs over one carbon atom, depending on how we want to use this in our conversion. So we go ahead and answer the question by taking the 431 carbon atoms that we started off with, and we're going to use the conversion factor. We want with the 12.01 AMUs over one carbon atom, and that's going to allow us to cancel carbon atoms. Remember, if you cannot cancel them, you don't have this set up correctly. So my answer is going to be in atomic mass units, or AMUs. It's the front number times the top divided by the bottom. In this case, it's divided by 1, so just 431 times 12, and you get 5,176 AMUs. So if I have 431 atoms of carbon, it's going to weigh 5,176 atomic mass units. Now let's look at an exercise that's going to help us with our homework. It says to calculate the mass in atomic mass units of 75 atoms of aluminum. So we're going to start with 75 atoms of aluminum. But I want to change that to atomic mass units, so I need a conversion factor. That conversion factor comes from the periodic table. So if you look up aluminum, you'll see that one aluminum atom is going to be 26.98 atomic mass units for one. So you're going to take that and you're going to put atoms on the bottom so that we can get that to cancel out, and our 26.98 AMUs on the top. That's going to allow that to cancel and that to cancel. So all you have to do is take 75 times 26.98, and we end up with 2,023.5 atomic mass units. That's how many atomic mass units that 75 atoms of aluminum is going to weigh. So when we look at this, these types of problems, it's getting this information off the periodic table that is so very important. One of the rules I want you to follow when you get the atomic mass off the periodic table is to round it to 2 places past the decimal. Round it correctly, but 2 places past the decimal is what I want us to get into the habit of rounding to.